Okay, so we just had talked about quantum mechanics, and we're now leaving quantum mechanics behind pretty much for the rest of the semester. Hooray, right? Except you don't get to see really cool things like the spectrum and colors of different elements, right? I think that's cool, right? I think that's cool. The first time that happened to me, it was a life-changing experience, literally. I mean, it made me really think about the universe and how it was run and how things went. So it was a really profound experience for me, and maybe for some of you it was, maybe not. Maybe it was just something they had to do to get through the class. I don't know. Be that as it may, we will move on, and hopefully some of my excitement about this stuff will rub off on you a little bit. The curiosity and the discovery. And we're going to talk now about laying the foundation for laws that we use every day in respiratory therapy, particularly the gas laws. But before we get to the gas laws, we've got to talk about the foundation. And the foundation of all the gas laws is actually derived from classical mechanics. And before I get too far into that, I just want to make sure we're okay on the basic states of matter. We have three major states of matter that we deal with in the day-to-day world. And what are those three states of matter? Solids, liquids, and gases. Okay? Each state of matter is very unique in the way that it works. Solids, for example. Solids don't flow at all, do they? Typically. Okay? Typically a solid doesn't flow. Typically the atoms are a little closer. The atoms are arranged. They have a very specific arrangement in solids. And those atoms are subject to what we call significant intermolecular forces. Right? Or what is known as van der Waals forces or van der Waals forces, or however they announce it. I call them van der Waals forces, so it is what it is. And these include things like dipole-dipole interactions, hydrogen bonding, right? Proteins, for example. That's a big thing there. You guys all talked about hydrogen bonding in chemistry, right? And we even talked about it last semester in pharmacology, how important it is when we talk about water, right? Because that's what makes water liquid, actually, is the hydrogen bonding. So solids and to some extent liquids actually have significant intermolecular forces between the different molecules and atoms and so forth, so on and so forth. London dispersion forces as well are part of the van der Waals forces. Gases, however, are a little different, aren't they? Most gases don't have a whole lot of intermolecular forces. There are, right? It's inescapable. Gases have electrons in them, right? They have protons. There's charge moving around. You're going to have some interaction occurring. But in a gas, that interaction is minimal, and the gases are spread out a lot more. Would you guys agree? And it's from that understanding of the three states of matter that we can develop a kind of a classical understanding, particularly of gases. And that classical understanding is something known as thermodynamics. And you guys all had to talk a little bit about thermodynamics in chemistry, correct? Of course you did. I know you did. I probably took the same chemistry class that you guys had to take, right? Either the 110G or whatever, and then there's the 111 if you went on, took the other semester of it. But well, what have you? Thermodynamics is kind of interesting, and thermodynamics is a study of all the laws and concepts that dictate kind of the conversion of energy from one form to another. And we talked about earlier, energy isn't destroyed or created, it's always there. We're just transferring it into different forms. And really thermodynamics looks at what happens in the transfer and kind of helps explain energy transfer. So let's just make sure we're okay on the basic terminology of thermodynamics. Energy, everybody's okay with what the concept of energy is. It's ability to do work, right? It's ability for some system to do work. And then we have another concept known as internal energy. And the internal energy of a system, a collection of gas, if you want to look at a system could be many things. For respiratory, it's almost always a collection of gas. is nothing more than potential plus kinetic. Oh, wait a minute! Didn't that whole concept kind of play into quantum mechanics, like the Hamiltonian operator, kinetic and so you see, there are a lot of concepts in classical mechanics that get modified a little bit for quantum mechanics, but they're still there. So internal energy, U is sometimes how it's symbolized, equals E, which is kinetic plus W, which is the or E is potential kinetic W. Heat. What is heat? Heat is hot, right? It feels hot. Well, what do I mean by heat? What's going on? Well, heat is a very special type of energy transfer. Heat is a transfer of energy from one system to another that results in a change in temperature. Okay. When we talk about temperature, well, I'll get there. I don't want to go into it quite yet. Like I said before, thermodynamics is a classical idea. It came from classical mechanics, and the real reason that thermodynamics was designed was to help during the Industrial Revolution. What kinds of engines were we making in the industrial? What powered the Industrial Revolution? Steam engines. Steam engines were big, and thermodynamics was primarily kind of came about because we wanted to be as efficient as we possibly could with steam, and we knew that steam involved transfer of heat and all this, and so we have the Industrial Revolution to thank for all of our thermodynamics knowledge, or at least the foundation of it. Okay. So thermodynamics is kind of cool because it looks at the big picture. So when we talk about quantum mechanics, we're looking at a very small piece of the picture, aren't we? We're talking about really small objects, electrons and nuclei and so on. Thermodynamics says, hey, you know what? In the real world, we have big systems with millions and billions of particles, right? And does it make sense to look at a single particle all by itself? Well, it does in some sense, but does it really help us in a lot of things we do in respiratory therapy? No, because big things are happening, right? People are taking big breaths and lots and bulk movement and so on and so forth. So thermodynamics looks at what we call the macroscopic properties of things. And what I mean by macroscopic is I mean a large average kind of value. And these properties are what we call macro state variables. Macro state variables. State variables. Okay? So what are concepts that look at macroscopically, look at the average state? And let me just ask you, what if you wanted to know about what was going on in this room right now? What are some things that you could test, you could measure to find out about what's going on in this room? Temperature, right? Does temperature really necessarily apply to like a single electron all by itself? And I'm like, I want to know the temperature of that electron. Does that really mean much? There we go. But how about a gazillion atoms of gas inside of a room like this? Do I want to know about every single individual molecule of gas in this room? No, there's no way we could. But what we could do is we could say, hey, on the average, what's going on in this room? So I take the temperature, right? And it's 72 degrees Fahrenheit, or it could be 22 degrees Celsius. Okay? Does that temperature, does that mean that that's the temperature of every single atom in this room? No, it's just the average. On the average, this is how much kinetic energy the molecules in the room have, on the average. Some may have more, some may have less, but in the bell curve, on the average, the kinetic energy of the particles moving around this room is this. And in fact, that's what temperature is a measure of. Temperature is a measure of average kinetic energy, not specific. Temperature is not looking at a specific atom, it's looking at the average, the collection of gas, if you will, in this room as a whole. Okay, how about pressure? Is pressure looking at a single atom or a single electron? No, pressure is another macrostate volume variable, right? Pressure is the average, not the kinetic energy, but the average potential energy density, right? So here I have temperature tells me about kinetic energy, and pressure tells me about potential energy. Again, pressure is the average amount of force that the gas molecules in this room are exerting when they hit something, right? Force over area. Remember, that's what pressure is. Force applied to an area. Okay. Again, a macrostate variable. How about volume? 1 liter, 2 liter, 3 liter, 4 liter. Is that a macrostate variable? Are you looking at the bigger picture when you look at a certain volume? Absolutely. So pressure, temperature, volume? Absolutely. And from thermodynamics, we can explain our gas laws. I just want to briefly talk about the laws of thermodynamics, the 3 laws, the important ones. There's actually a 0th law, which is kind of stupid, so I won't even go over it because it's so ridiculously stupid. Why would you ever even say that? But there are 3 laws that are not as ridiculous. The first law of thermodynamics says that the energy of the universe is constant. We already knew that, right? It's not created or destroyed. It's just transferred into different forms. The second law says that all systems tend to move toward disorder or randomness. And the measure of disorder or randomness in a system is known as its entropy. Entropy means many things. If you guys are involved, anyone here been involved with computers and information and things like that, entropy has a very intimate relationship with information. But for this class, let's just say that it's kind of a measurement of disorder. And what do I mean by that? Well, let's imagine that I have a gas tank here, okay? And I put some gas molecules in it, and I put all those gas molecules down here in the corner. What are those molecules going to want to do? They're going to want to diffuse out, right? Like this. That is entropy. When those gas molecules are close to one another and kind of packed up, that's lower entropy, right? There's less disorder. Does that make sense? They're kind of ordered up, they're packed together. And then when they diffuse out, they spread out everywhere, that's more entropy, right? They're more disordered. They're all over the place now. So does that kind of intuitively make sense of what's going on there? And when you, like, for example, take this room. Would you expect every single molecule of gas in this room to spontaneously move all into this room here and then leave nothing but vacuum here? Would you expect that to happen? No. That would be moving from higher entropy to lower entropy. We'd never see that, right? Anyone drop an egg? What happens when you drop an egg? It splatters everywhere. Have you ever seen a splattered egg reassemble itself back into a nice egg? Have you ever seen that? No. We only tend to see things move from low to high entropy. Now, can we make things move from high to low? Yes, but what is the cost of doing that? Costs energy, and when I'm using energy, I'm transferring heat, I'm increasing temperature, and what am I doing to entropy? I'm increasing entropy. There's no getting around it. The entropy of the universe is increasing and increasing, and it will continue to do so until the universe is cold and dark and at a maximum level of entropy. Okay, the third law, that's kind of a sad way for everything to end up, huh? But that's what it's looking like. The third law says that there is no entropy or molecular motion at 0 degrees Kelvin. 0 degrees Kelvin is an interesting temperature. And I should expect you guys know what Kelvin and Celsius and Fahrenheit are, because we talked about those in other classes. 0 degrees Kelvin is a theoretical temperature known as absolute zero. Have you guys ever heard of that term, absolute zero? And it is a theoretical temperature where there is no more thermal motion. And at that temperature, every atom, molecule, what have you, would be at its lowest entropy, it'd be at its most orderly, and that's that. what we found is we cannot reach absolute zero in any practical sense. Okay, is it unattainable? We can't obtain absolute zero in a practical sense, at least. We can get really darn close. We can get really close to it, picokelvin within it, but we can't quite. I think there's some quantum experiments where if you interpret them a certain way, you can get to absolute zero. But in a practical sense, in the real world, ain't gonna happen. Okay, so those are the three laws of thermodynamics, and then there's something called Maxwell's Demon. And you guys remember who Maxwell is, right? Or was? He came up with Maxwell's equations of light, of electromagnetism. Well, he also was working on thermodynamics because he lived during the Industrial Revolution. And he was probably next to Isaac Newton. He was probably the second greatest physicist this world has ever known. Isaac Newton being number one, at least on my list. Isaac was number one. Maxwell's probably number two. And then, of course, our pal Einstein was probably number three. If I had to, put a gun to my head and say, you better choose, Chris. And what Maxwell did is Maxwell came up with a thought experiment. He said, hey, let's say that I take two systems here. Okay? I take two systems. I have a system with a lot of high energy gas molecules. The kinetic energy is high, so the temperature is going to be... Kinetic energy is high, the temperature is going to be...
The more kinetic energy...
Remember, what is kinetic energy a measure? What is temperature a measure of?
Kinetic energy.
Average kinetic energy, right? So more kinetic energy, more temperature, right? They're going to be hotter, they're going to be moving around faster. Everybody's okay there. That makes sense. Okay. So I have these really hot, fast guys here, and then I have these cool, slower guys over here. And I have a door between these two systems. If I open the door up, what's going to happen?
They're going to diffuse.
Okay. Is the cold going to go the hot, or what's going to happen?
Probably both.
Okay, there's going to be some mixing, right? Okay, there's going to be some mixing. But let's just say that there are some hot molecules in here, just a few, and maybe a few cold molecules in here, right? That make sense? And we would still expect them to kind of mix and match, and then the temperatures would equalize, right? And that would be a higher entropy, right? So this one would get warmer, and this one would probably get a little cooler, right? Everything would kind of mix up, and that'd be cool. Well, what Maxwell said is, hey, what if there's a little demon? What if there's a little demon? Let's see if I can find a different color here. A little demon who came along, and that demon put a little door here, and that little demon sat here with his little demon horns, his little demon pitchfork, and said, I am only going to allow these hot guys on the cool side to move over to the hot side. Would that normally happen? No. What we normally see happen is the hot would go to the cold, right? But he said, no. I'm only going to open the door when I see this little hot guy here. When this little hot guy gets close to the door, I'm only going to open it. And I'm going to open it. I'm going to let the hot one through. And what's going to happen to the cold side? Is it going to get warmer or cooler now? It's going to get cooler, isn't it? And that's what Maxwell's demon is. And what Maxwell realized was that for eggs to reassemble themselves, for things to get more disorderly, for entropy to decrease, something had to intervene, right? Something had to say, no, I want to do this. And the only way that something could, a human being or an organism or what have you, the only way it could is by using energy. But what happens when I use energy? I release heat, and what happens then? The overall entropy still increases, right? And the analogy that I use, if this Maxwell's demon doesn't make as much sense, is let's say that I want to make the entropy a little lower in this room. I could cool it off, right? So let's say I put a big old air conditioner there and I cool the room off. Have I decreased the entropy? Well, I hear, but what has that air conditioner been doing?
Spinning.
Being allotting energy, and what gets blown out of the back of an air conditioner? You guys, heat. It's really warm, right? So the overall entropy is still increasing. Does that kind of make sense? Okay. All right. So that's that on the home stretch. So from thermodynamics came a theory, and then from that theory, all of the gas laws followed. That theory is known as kinetic molecular theory, or KMT. Kinetic molecular theory, KMT. All right? Kinetic molecular theory looks at the macroscopic behavior of gas, okay? Not individual gas molecules, but the macroscopic behavior. What does thermodynamics look at? The same thing. So thermodynamics, so I have classical mechanics here, and from thermodynamics comes KMT, kinetic molecular theory. It's derived from thermodynamics. Thermodynamics, of course, is classical. There are 6 postulates of kinetic molecular theory, and I would want you guys to know these postulates as well as the laws of thermodynamics. So the first postulate says that gas is a collection of many, many particles, or molecules. And these molecules move in straight lines, okay? And they more or less obey Newton's laws, F equals ma. They have kinetic energy. They can have potential energy. And they move around with random motion. Okay? Now, is that really the case? No, that's not really the case, because quantum mechanically there's a whole lot of funky business going on. But when we look at large collections of gas, do they pretty much behave this way? That they're a large collection of molecules or particles moving around in straight lines that more or less obey Newton's laws? Yes. Okay. So again, macroscopic. The second postulate says that individual particles of gas don't occupy space. Okay? They're tiny. They're tiny little points. They don't really occupy space. And it's only when we have a large collection of these molecules do I actually have space occupied. That makes sense, right? Because again, thermodynamics doesn't look at a single particle or a single electron or what have you, right? Thermodynamics is more concerned with large collections. So that makes sense that kinetic molecular theory, the second postulate, would be a collection. So the collection of gas will occupy a certain volume, but not a single molecule. The third postulate states that when gas molecules collide, they do so with a perfect elastic collision. And they have perfect conservation of energy. The reason that has to be is the following, and I don't have one, but if I drop a ball, okay, I take a ball here, and I drop that ball and hits the floor, what happens? It bounces. Does it bounce all the way back up to my hand, though? No, it just bounces up a little bit. Why? Because when it hit the floor, it transferred some momentum to the molecules on the floor, right? And that area of the floor is a little warmer than the rest of the floor because those molecules are moving a little bit. And anyone ever hammered anything for a long period of time? What happens? It gets warm, right? Because you're transferring energy. Now, what if gas behaved that way, though? What would happen?
It would heat up everything.
Right. I have this tank of gas here is under pressure, right? It's 2,300 psi. So if gas behaved like a ball, a rubber ball, every time a gas molecule smashed into the inside of this tank, it would release its energy, right? And then this tank would get warm, and then it'd radiate all that energy away. And what would happen to the pressure over time? It'd decrease, right?
Oh,
because all of this energy would be radiated off, right? But do we know that to be the case? If I have this at 2,500 psi, or well, just under, it'll pretty much stay there, right? Pretty much stay there. The gas does not lose energy. So that is the third postulate, perfectly elastic collisions. An inelastic collision, like a ball hitting the ground, there is a transfer and there's a loss of energy. But when we talk about gas molecules, they're perfectly elastic collisions. There is no loss of energy. The fourth postulate says that there are no intermolecular forces between individual gas molecules. Again, we know this is not the case. We know that at a minimum, London dispersion forces do exist, right? Because electrons move around, right? Electrons move around, and you can have these temporary poles, and you're always going to have some type of London dispersion force at a minimum occurring. But for the most part, the gases that we work with at least, don't really experience intermolecular forces. For the most part, on the average, they don't. And then the fifth postulate is the average kinetic energy of the gas can be calculated by the formula 3K, which is a constant, times the temperature divided by 2. That's the average kinetic energy in joules, the collection of gas. Okay, and gases that follow these 5, I think I said 6, didn't I? 5, I'm sorry, 5 postulates. Gases that follow the 5 postulates are known as what kinds of gases? Huh? They're known as ideal gases. They're ideal. They behave. Now, are all gases ideal? No. Are any gases ideal? Not perfectly ideal, but most of the gas that we work with is ideal enough. How does that sound? Right? Just like, is there any perfect human being? No, but most of us are perfect enough, right? And that's kind of the way I look at it. Is nobody's perfect, but we're perfect enough. We do human being things on the average, right? Gas is the same way. There's no perfectly ideal gas, but there's gas, it's ideal enough. Now, some gas like carbon dioxide, where there are really significant interactions that occur with CO2, we know that CO2 forms H2CO3, which is carbonic acid, and that carbonic acid can break down and reform, right? So CO2 is actually kind of a bad example of an ideal gas. But oxygen, O2, nitrogen, N2, helium, argon are all very good ideal gases. Okay, and so most of the air that we use and most of the air that we'll be using in IPPB, IPPV, ventilator circuits, things like that, it's ideal enough that we can say that it obeys the 5 postulates. Everybody's okay there? So again, this is one of the things of science that I really want to focus on, is that this is a model. It's a model of how the universe works, but is it exactly how the universe works? No. Okay? No. It's not exact, but it's a model, and the predictions that it makes are so good that the wiggle room, the fudge factor that we add, it's okay, right? It's okay under most circumstances. Now, when we start talking about these really quantum mechanical things and bizarre effects, then we have to use other things, right? But at least for this class, we're okay with kinetic molecular theory. Everybody's okay there? So that leads to gas having 2 fundamental properties. It's very different from liquids and solids. Even though liquids and solids to some extent can do this, they don't. It's so little that we just say they don't. And that is, gas has the ability to expand, or expandability, and it has the ability to be compressed, or what we call compressibility. It can expand and compress, and we typically can't do that with other states of matter, like compressing solids and compressing. You ever try to compress water? Can you do it? No, it's incompressible. Well, it does a little bit, but it's so minuscule, it just doesn't really matter. So that leads, from all those 5 postulates comes the mother of all gas laws. So what did I say? It's a law you guys have used before. It's nothing special. You just now know where mom's name comes from. You learned a little bit about your family history, your family tree. So mom So if mom comes from classical mechanics and mom comes from thermodynamics, so mom's great-granddad was classical mechanics. Granddad was thermodynamics. Dad is kinetic molecular theory. And what do we call gases that more or less obey all of these? Ideal gases. There we go. So mom's name is the ideal gas law. That's mom. And the ideal gas law, I don't have it in your notes. You guys remember? Does anyone remember what the ideal gas law is? It's PV equals. Anyone remember? No? Anybody? Okay, PV equals N. Oh, that's a horrible N. Let's try it. PV equals nRT. All right? The pressure times the volume of the gas equals the number of moles times the gas constant R times its temperature. PV equals nRT. And from mom come all the other gas laws. Comes Boyle's law. Comes Charles' law. Comes Gay-Lussac's law. Comes Dalton's law. Comes, to some extent, Graham's law. All right. Comes the combined gas law. Okay. These are all her children, but they all come from mom. So, mom. PV equals nRT, the ideal gas law. And we will not start dealing with mom and her kids. They're an unruly bunch and involves a little bit of math. You guys remember, right? A little bit of math. But we will start dealing with mom next week in the next lecture. Okay, guys? And we're done a little early. I hope nobody has any complaints about that. All right, get out of here.